Hello class. We're not really moving on to a new unit. I'm just going to call this day 12. It's integration by U-substitution. So we've done a lot of antiderivatives and integrals lately. This is the next step. It's kind of doing the reverse of chain rule. So we're going to be taking derivatives, antiderivatives, or integrals of functions, and they kind of look weird, but they come from what would have happened if we took a chain rule for a derivative. So what we're going to do is take our original integral and we're going to substitute in a u for like a complicated part of it, and that will help us simplify the integral. So we have to determine what the u is, we have to rewrite it, we have to find the antiderivative. Remember, these are just general antiderivatives, or indefinite. So we have to do a plus c at the end, and then we have to rewrite it not with the u, but with the x. Let's go through an example. So as you see in number 1, I have this really messy integral of 15x to the 4th, parentheses, 5x to the 5th minus 2, all raised to the 3rd power. I could try to expand it all and get this huge polynomial or this and that, or let's look at using u is equal to that 3x to the 5th minus 2 inside the parentheses. Because when we take this derivative, or what I call the du, it becomes 15x to the 4th, and because this is an x, I have a dx. And then I look here and I'm like, wow, that is what I have in the problem. I have a 15x to the 4th dx. And that could go away, and that becomes du. And this part here is the u, and I can rewrite this as u to the 3rd du. And now it's a much easier antiderivative to take. And it becomes 1/4 u to the 4th. Don't forget your plus c. But I can get rid of the u and rewrite it as 1/4. U stood for 3x to the 5th minus 2 to the 4th plus c. That is the integral, or the antiderivative, of that messy thing that we had to begin with. If I started with this function and I want to take its derivative, I would use chain rule to take its derivative because I have a function inside of a function. So this whole U-substitution is doing it in reverse. So for the next one, I give you the u, 4x to the 4th minus 5, because that's kind of inside. I take its derivative. I get du equals 16x cubed dx, but I really want negative 16. So what should I do to this to make it negative 16? I should multiply by negative 1. I get negative du is equal to negative 16x cubed dx. And then all of a sudden I realize I have what I want, and I can rewrite this problem as the integral of negative u to the negative 5th du. And now it's a much easier thing to do. Equals 1/4 u to the negative 4, because when I take an antiderivative, I add 1 to the exponent, plus c, or 1/4 4x to the 4th minus 5 to the negative 4 plus c. All based on this u-substitution, which I made you do when we did chain rule. Now we're kind of doing it in reverse. So here I am on the next problem. I've decided that the u is 5x squared minus 3. I take its derivative, so du equals 10x dx. But I really want 20x, so I'm going to multiply by 2. I get 2 du is equal to 20x dx. And there we go. I have those right there. This stuff becomes a u, so I have, it now becomes 2 cosine u du, and this is a much easier antiderivative than before. Change color. I get equals 2 sine of u plus c, or 2 sine, and the u is really just 5x squared minus 3 plus c. As you can see, this little manipulation of putting in something a little bit complicated, and for the u, helps me get rid of something else in the integral that I need to get rid of to make my life easier. Right now I've been nice. I've been giving you the u value. We'll talk about when I don't. So for this next problem, I set my u equal to 4x cubed plus 3, and I got du equals 12x squared dx, but I really want 36x squared. Multiply. Wow, that's just terrible. Does not like my hand right now. Multiply by 3, and I get 3 du is equal to 36x squared dx. And look at that, I had those two right there, and I could rewrite this as the integral of 3 e to the u du, which is a very easy antiderivative to take. Not very complicated at all. 3 e to the u plus c, or 3e, not to the u anymore, 4x cubed plus 3 plus c. So now I'm not giving you the u. We have to figure out what our u for the substitution should be. So here's my little hint. The u should equal something. So du equals something. So we will eliminate something else. In other words, when I take the derivative, that should help me get rid of something else in the integral problem that will make the problem much easier. I would always say you always take a higher degree of x, because when we take its derivative, we get a lower degree of x. So if I do this example, and say my du is equal to 5x to the fourth plus 1, and when I take its derivative, I get du is equal to 20x to the third dx. I'm like, well, that's not too bad, because I have, look at this, I have 10x cubed dx. So all I really need to do is multiply by a half. I get a half du is equal to 10x cubed dx, which is what I wanted. So I can rewrite this problem as 1/2 times, well, 5x to the fourth plus 1 is in the denominator, so times 1 over u du. And that's what I get. So when I take this antiderivative, well, it's going to be 1/2. And again, the antiderivative of 1 over u is ln of u plus c. And when I clean this all up, I get 1/2 ln, and the u is just 5x to the fourth plus 1 plus c. A little bit more complicated. You have to figure out what the u is going to be for you. But a lot of times our rule of thumb is maybe it's something inside of parentheses, or maybe it's a term or an expression that has x with a higher power in it. It just kind of takes some practice and kind of what I call seeing the forest through the trees. Again, like I said, I tend to like rule of thumb as maybe the u is something inside of parentheses, because now I can rewrite this when I do all the work, and I realize it's just going to be, wow, that's terrible, -2 u to the 2/3 du, because I got rid of all those x's by substitution. And then when I take its antiderivative, well, I'm going to get, this becomes u to the 5/3. And then I got to think, well, if this is u to the 5/3, that means I need the reciprocal of that, or 3/5, times the number up front, which is -2, which is -6 over 5. So when I do all this, I get a negative 6 over 5 u to the 5/3 plus c, or negative 6 over 5 parentheses 4 minus 5x to the 4th to the 5/3 plus c. So again, okay, sorry about that. So again, the u is the stuff inside the parentheses, e to the 3x minus 5. E to the 3x is really a chain rule, but it's a mini chain rule. We've done it enough that the derivative du is 3e to the 3x dx. I really want 6, so I multiply everything by 2. And I can rewrite this as integral of 2 sine u times du, because I can get rid of all that other stuff, and the antiderivative of all this, antiderivative of sine is negative 2 cosine u plus c, and I can rewrite this as negative 2 cosine, and the u is really e to the 3x minus 5 plus c. Again, this looks very complicated to begin with, but at the end, we figure out a nice simple u substitution to clean things up. It got rid of a lot of things that were in the way. Okay, for this next problem, I decided the u is going to be 5 plus ln of x. Its derivative is du is equal to 1 over x dx. And it's hard to tell, do I really have a 1 over x dx in this problem? I do. If I rewrite this, this is integral of 5 plus ln of x to the 5th times, since x is in the denominator, it's really 1 over x dx. And now I actually have what I wanted, so I can rewrite this as u to the 5th du. And taking its antiderivative is 1 over 6 u to the 6th plus c, or 1/6 parentheses 5 plus ln of x to the 6th plus c. Actually, once you figure out what the u is, it's really like a two-step process after that. It really cleans up quite quickly. So as you can see, I've chosen my u to be 5 minus 2 e to the 4x. And if I work through this and take its derivative, I get negative 8 e to the 4x. Same little chain rule that we did before with e raised to a power. I really want 12 e to the 4x. So I have to think, how can I change a negative 8 to a 12? Well, all I did was do 12 divided by negative 8, and I realized, oh, I just multiplied by negative 3 over 2. And I get what I want, I rewrite it, and this antiderivative is going to be negative 3, well, I don't know about that, negative 3 over 2. It's going to be u to the 5/4 when I add 1, and I got to realize, well, that reciprocal is 4/5 times my number up front, negative 3 over 2. I clean it up, I get negative 6 over 5 plus c, and then I could clean it up and do negative 6 over 5. U is 5 minus 2 e to the 4x raised to the 5 over 4 plus c. That is its integral or antiderivative. Like I said, once you figure out what the u is and how you manipulate it a little bit, maybe you got to multiply, things clean up quite quickly. And on to our last example. I've rewrote it first. I can't really do it with roots, so I rewrote it as 2x squared parentheses 2x cubed minus 3, all raised to the 1/2 to represent the square root. U is that 2x cubed minus 3, its derivative of 6x squared dx, but I really want 2x squared multiplied by 1/3. So now I have the integral of 1/3 u to the 1/2, and I realize, well, let's see, u to the 1/2 has to be u to the 3/2. That reciprocal is 2/3 times this number up front of 1/3 gives me 2/9 u to the 3/2 plus c, or better yet, 2 over 9. My u being 2x cubed minus 3 raised to the 3 over 2 plus c. And there is u substitution for integrals.